right, if you guys are tuned in, let me know if you got any questions. I got some people joining here. It's kind of hard to tell if you're trying to send me a question. There is this little Q&A app. I thought I enabled it. Sorry.
Oh God.
I'm hearing some voices out there. If you got a question, let me know.
Hi, Mr. Thompson.
How's it going? How's the studying going so far?
Good. How's life?
Life is good. Yeah.
That's
How
good.
about you? How's your life right now? You feeling overwhelmed with all your finals?
Oh, especially math and physics.
When do they take? When do those tests happen?
I had physics today, and math is on Monday, so it's gonna be fun. Fun weekend.
Yeah. One of those double-edged swords. It's nice to have the extra time, but it ruins your weekend.
Yeah.
Yeah. Well, we've got 1, 2, 3, 4, 5, at least 6 people joining us so far. Anybody have? Oh, that's 7. Anybody have any questions? All right, I tried to set up this Q&A, and it says it's disabled. I don't know why. All right, there we go. Anybody have any questions? It looks like I've got a little bit of a chat going on here too on the side. Anybody have any questions? It's awful quiet out there.
Do you have any like hard questions that we can do right now?
Hard questions. Well, I guess the one disadvantage to like the chat format here is it's hard to work out like sort of math problem questions or conversion questions. But maybe if you wanted to think about the concept of ionization energy as it relates to calculating the value for the ionization energy based on, I'm trying to think of the correct phrase, based on convergence of the limit in the ultraviolet series. So when an electron in hydrogen leaves from n equals 1 all the way to the infinite energy level, that is the ionization energy. And if we know the wavelength of that light, we can calculate the ionization energy and compare it to the ionization energy that's listed on the periodic table. Let me see if I can find, I'm going to try to see if I can find a diagram that I can share. See if that helps. I think I can share diagrams. Yeah, Kunwu, I see the message. I'm working on screen share. What I want to find is a diagram. Let me see if I can find a diagram that would help with this question. HS Tech. I agree. I'm looking. Okay, let me try. I'm going to try screen share. Let's see if it. All right, I don't know if you can see this, but I've got a a page up. Might be a little bit slower. Oh yeah, can you see that?
Yes, I can see that.
Yeah.
Okay, so here we've got, in this diagram here, we've got the different series for hydrogen. And I don't care about the names of the series, the Lyman, the Balmer, and so on. But remember that if it's falling from a higher energy level down to n equals 1, it's going to be in the ultraviolet. If it's falling from a higher energy level to n equals 2, it's going to be in the visible series. We can actually see that spectrum. If it falls to n equals 3, it's going to be infrared. And we're not going to worry about these other ones. So the opposite is if it's at a lower energy level and it absorbs energy, it's going to go to a higher energy level. And if I can get an electron to go from n equals 1 and essentially leave the atom, that's the equivalent of going from n equals 1 to n equals infinity. If you remember that each of these transitions involves a specific wavelength of light that is either emitted or absorbed. And if I know the wavelength of light, I can calculate the energy of that photon, and I can multiply by Avogadro's number to find the ionization energy. This is from topic 2 or topic 12. I don't remember which topic it was from. But it essentially uses the relationship. If you look at the data booklet, and let me grab the data booklet. So here's the data booklet. I go to the equations. The first equation we're going to use to solve this problem is right here. C equals frequency times wavelength. So if I know the wavelength, I can calculate the frequency. The second equation I'm going to use is here. E equals h nu. E equals h times the frequency. The frequency we just calculated by using this equation at the top because we know the wavelength. And if we scroll to the next page of the data booklet, here is Planck's constant. That's h. So that means I can calculate the energy of that photon that would be absorbed. And I'm going to try something here. It's not going to be perfect, but hold on a second. So what I'm trying to do is set up a clean Word document so I can type some formulas for you. Okay, so Rid, I think it was you that asked the question. I don't know if it's making sense. If you asked me to kind of come up with a question, I don't know if it's making sense, but we have c, the speed of light, equals frequency times wavelength. And in a question of this sort, we typically know either the frequency or the wavelength. But in order to calculate the energy, which is h, lowercase h, times frequency, in order to calculate the energy, I need the frequency. If I'm given the wavelength, I want to calculate the frequency because frequency is the speed of light divided by wavelength. So for hydrogen, my memory is that it's 910 nanometers is the wavelength. Hydrogen. So 910 nanometers. Let's see, I got to do some math. 9.1 times 10 to the 8th. I don't have my calculator in front of me. That's the wavelength. So I can take the speed of light, which is 3 times 10 to the 8th. Divided by 9.1 times 10 to the 8th. And I hope I'm using the right wavelength in meters here. Something tells me I'm not. If I do that math, that gives me the frequency. Yes, thank you. Kunwu, thank you for that. Aiden, you ask, will the wavelength of hydrogen be in the data booklet? No, but it would be part of the question. You would be given the wavelength as part of the question. Or you would be given the frequency as part of the question. If you go back to our test on topic 2, so here's something I can do. I can find the question. Give me a second. This is going to take a second. Well, okay, a couple seconds. We had a test on this, and I've got a mark scheme. Let me find it. Here it is. So this is the previous question, but it'll give us some background. It says, deduce the electron transition required for the red line of the visible emission spectrum of hydrogen. The red line is the line that has the lowest energy of the visible spectrum, so it's got to be the smallest transition, so it's 3 to 2. It says here the turquoise line in the hydrogen emission spectrum has a wavelength of 486 nanometers. Calculate the energy of a single photon. So E equals, and what I did here is, instead of E equals H nu, H times frequency, I took E equals H times C, speed of light, divided by wavelength, because I substituted here for frequency. So Planck's constant is h, the speed of light is here, and I put, what I did here is I just took 486 nanometers times 10 to the negative 9th meters, because a nanometer is 10 to the negative 9th meters. And that gave me the amount in joules. And if I go back to the question, calculate the energy of a single photon. Okay? Stop me if you got a question, but what I'm going to do is move on to the next one, which is a little bit further along. The next one says, for an unknown element, light at the limit of convergence for the ultraviolet series from its emission spectrum has a wavelength of 2.30 times 10 to the negative 7th meters. Use this information to calculate the first ionization energy of this element and deduce the element's identity. So I'm using the same formula, and I get the energy of a single photon, and then I'm going to multiply it by Avogadro's number to get Bromont. And in this case, it was this answer would be in joules. I would divide by 1,000 to get kilojoules. So I got 521 kilojoules per mole, which happens to be lithium. So Rid, in terms of like a challenging question based on previous performance on the test, I think this would be an example of a challenging question that might help you prepare. So Rid, I don't know if that gives you an example of something, but let me know. Pim, you said, where is this document? So the document I'm showing on the screen here is a mark scheme for a previous test. And if I go, let's see, I'm going to put a new window up for you to see. If I go to Haiku, on Haiku, so give me a second to get to the chemistry page of Haiku. On Haiku, there is a link to, hang on a second, I got two screens going here. On Haiku, in the web link section, there is a folder for mark schemes, and it has all of the mark schemes for previous tests. So, okay. I don't know if this is going to mess up the Google Hangout, because I have to sign in with my ISB account, and I'm not using my ISB account for the Hangout. So if the Hangout hangs up, I'm sorry. I'll come back to it. But PM, I hope that helps in terms of you finding it. Here we go. I'm on my on the Haiku page here. It says Mark Schemes folder. if you click on that mark schemes folder, it has mark schemes for tests and quizzes, and at some point it might have like a folder for final exams. I find list view works better. So I've got the quizzes from topic 4, the quiz from topic 2, the test from topic 2, the test from topic 4. I haven't yet put up the quiz that some people took, the optional quiz, but I'll put that up as well. So PM, I hope that helps you find that document. And really all of you, you should be going back to these mark schemes anytime we take a test, and you should be looking at the questions you missed and trying to learn from your mistakes. Okay, so next question. You can type it in the group chat. You can unmute your microphone and ask it of us. I'm happy to try and work another question. It's hard for me to show you calculations, but I can try. It worked a little bit on that document. So let me know if you've got some questions. In the words of Fraser Crane, I'm listening. Okay, so for those of you that are listening, Leo asked on the chat, do we need to know about log ionization energy? And I think the log function in terms of making making a graph of the successive ionization energies is something to be aware of, but specifically log, that's just a way to show a really large range of data on a graph. As you do successive ionization energies, if you have enough electrons, those last few electrons can have really high ionization energies. And so let me do an image search for successive ionization energies, and let's see if we can find a graph and kind of make sense of this. This one, yeah, this one is in log. It's kind of small. Well, let me expand it a little bit. So this says log of ionization energy, and what's key here is it's not so much that it's a log function, but that I can see the major jumps. So here, between electron number 7 and 8, there's a major jump, and then from electron 15 to 16, there's a major jump. This has 17 electrons, so this would be chlorine. Rid, I see your question about the 10-person limit. Is there any way for me to change the limit? Let me know if there's a way to change the limit, and I'll work on that. I thought I made it public so that there wouldn't be a limit, but I don't know. Okay, Pam, I'll get to your question in a second. Limit is 10. That's too bad. I don't know how to fix. Well, maybe people can drop out when they feel like they've got a good handle on things, so that others can join. Leo, let me kind of finish your question, and then I'll move on to some of the other ones. So Leo, in terms of log, it's not specifically about the log as it is about the jumps. So this jump from 7 to 8, chlorine, if you think about chlorine, let me copy this image and take it to a Word document. If you think about chlorine, chlorine has 17 electrons. So 1s, 1s2, 2s2, 2p6. I'm not going to worry about formatting. 3s2, 3p5. So when it loses a successive electrons, it's going to lose these 7 electrons, and then it's going to go down to the second energy level. So there's a big jump between the 7th and the 8th electron. Now, after it loses those electrons, it's going to lose 8 more electrons before there's another large jump to go to n equals 1. So that large jump happens after 8 more electrons. So Leo, I hope that kind of answers your question. Pim wants to talk a little bit about solutions and dilutions. Aiden wants to know about specific definitions. That's an easier question to answer first. Pim, I won't forget about your question. Pim, no, you do not need to know Lewis base and Bronsted-Lowry acid. In terms of specific definitions, Aiden, I think if you were to go over that IB document, the spread Google sheet that I have created that has definitions, just to be familiar with them, I would say that if you look at your if you look at the previous tests and if you look at the syllabus statements, there are definitely some terms that could be asked in terms of just giving a definition. One of them is like ionization energy. Give the second ionization energy of barium or something like that. I think that's kind of a definition. Rahul asks about links to past IB exams. I don't have any links to that. Technically not legal for me to share those. I mean, I can share the ones I've got, but in terms of other people sharing them, technically not legal. I'm sure you can find them out there if you search for them. In terms of electron configuration of ions, I can do a couple of those. Pim, I haven't forgotten about your question about solutions and dilutions. I'm trying to handle questions that I can do shorter first and then come back to that. Janata, let me answer your question first, though, on how you identify an element from an ionization energy graph. Essentially, you can identify an element based on it is technically illegal just because it's they're copyrighted from the IB, and even I'm not supposed to publish those past papers, but I know they're out there. So anyway, Janata, answering your question, in terms of identifying an element, the key is to figure out where the major jumps are. The major jumps happen when you drop energy levels. So in the case of chlorine here, this graph that I have on my screen is chlorine. And if you notice, chlorine has 7 valence electrons. So that means that there will be 7 electrons before a major jump. And then there are going to be 8 electrons before another major jump. So you identify it by where the major jumps happen. So, Janata, I'm not sure if that answers your question completely. If I look at another element, let me see if I can find another element. Yeah, so let me work on that, Rid. I want to find one that I know is a good example. So this one, let's view the image. This one has a total of 13 electrons, and the total number of electrons might help in terms of trying to identify the element. You can't necessarily, so what element has 13 electrons? And if we want to know that, we can go to our trusty periodic table. So 13 electrons is aluminum. Now let's see if that makes sense. Aluminum has 3 electrons in its outer shell. And here, there are 3 electrons before the first big jump. Yeah, Pim, your question about major jumps happening when there is a change in energy level. Yes. Small jumps happen during a change in orbital. Yep, that's exactly right. So aluminum has a 3p electron and then 2 3s electrons. And then it has 2 p electrons and 2 s electrons and then 1 s electrons. So those major jumps happen when I drop in an energy level. The major jumps in ionization energy happen when I drop in energy level. Pim, tell Pauline we're sad she's not here too, that she's left out. We might have to, I don't know if there's a better way to do this. We'll maybe have to try a Skype group chat or something. I don't know. It seems like there should be a way to make the video public to everybody. I don't know if it's because of the way I set it up. Aiden, in terms of that small jump, the small drop when a half full orbital becomes not half full, I don't know if what we would probably have to do, if you look at this graph for aluminum, it goes all the way up to over 200,000. So we would really have to graph these ionization energies on their own graph so that we could spread them out and see if there's that drop. Where you're thinking about like these orbitals, your question in my mind relates more to ionization energies across a group, and like this graph. So this is across period 3. So I have sodium and magnesium. This is not successive ionization energies now, this graph. This graph is different elements. So sodium is argon 3s1, magnesium is argon 3s2, but aluminum is argon 3s2 3p1. So this 3p electron that's being removed, is further away from the nucleus than the 3s electron, so there's a drop. This is called a discontinuity. This silicon is 3p2, phosphorus is 3p3, and then the next discontinuity is sulfur, because it now has a paired electron in one of those p orbitals, which means there's a bit of repulsion, which is going to make that electron easier to remove, and then it keeps going up from there because I keep having more protons that are going to hold those electrons tighter. The radius is decreasing here. So I hope that answers the question in terms of Iden, in terms of clearing that up. RID, yeah, pretty much magnesium would have a jump from 2 to 3, and then it would have another one after another 8. And then the last 2 electrons would be quite high. Live stream. Kunwu asked if a live stream would be better. Yeah, might be a better idea. Kunwu, what HS Tech coming through here? What do you recommend? I'm certainly willing to give it a try. So I don't know if there are more questions. Kun was looking up free live stream broadcast sites to see if we can try something like that. So Pim, tell Pauline we're working on it. Pim also asked a question about solutions and dilutions. Pim, can you give me a bit more specific, of a question? And in the meantime, I'm going to send a quick tweet out to let people know we're working on a different solution. So give me a second here. Okay. Iden gave me a link here. Let's see if I can try that. Whether you're recording a concert, a sports business talk show, or just yourself, enable live streaming. Okay, so those of you on the Google Hangout, be aware the Google Hangout might end up closing. If it does close, I'll give a new link through Twitter, so through the hashtag. So give me a second. I'm going to see if I can make this YouTube link that Iden gave. Okay, so for my Google Hangout, it says 0 people are watching. Is there a way for you to watch but not be part of the chat?
Since it's like part of Google, I think you can live stream this Hangout.
Through the YouTube, Rid?
Yeah.
Okay. Well, I'm trying to get that to work.
So like people who watch won't be able to talk or chat.
Yeah, but they can send me questions through Twitter, for example.
Yeah.
It's looking like yeah. So that'd be one way to do it. It says here. Okay. It looks like it's. Let me just see if I can find a link. Oh, hey. I might be watching myself now. Hold on. Give it a second. Thanks for your patience. Yeah. I'm watching myself now. I'm going to give you a link in a second here. This is crazy because there's a little bit of a delay between when I talk and when I hear myself talk. Oh, I just put up a tweet and I forgot to give the link.
Mr. Thompson, is like there's a dip between MG and AL, and is that because there's like a new orbital in AL? Like.
Okay, hold on 1 second, Rid, because I'm actually using the YouTube to watch to see if it's going to work, and then it's actually playing my sound. So hold on. I have two conversations going on in my ear. One is the delay, and one is the actual original chat and your question. So, okay, so I put up. Yeah, Kunwu and Leo, thanks for doing that. And Rid, there is a link that I just put up on Twitter that should be a way to watch it on YouTube, but it does prevent you from asking questions directly. So you can use Twitter. I'll try to check Twitter as much as I can. So, okay, Rid, you were starting to ask a question. Yeah, I did that. I finally muted myself on the stream so I don't have to listen to myself twice. Thanks for that. Rid, why don't you try your question again?
So, in the first ionization energy, AL is smaller than MG even though it has more protons?
Yes. And the reason for that, so what I'm going to do is put that into a Word document so that I can talk about it a little bit better. So here's hopefully you can see on the screen, here's the first ionization energies. And if I look at magnesium, magnesium is neon 3s2. Aluminum is neon 3s2 and then 3p1. So that 3p electron is in a higher it's not in a higher energy level, but it is in an orbital that has higher energy. So the 3p electron is easier to remove than a 3s electron, which means even though the aluminum has an extra proton, it still is easier to remove that electron because it's in a 3p orbital instead of a 3s. Now, when you go to silicon, the electron is being added to the same type of orbital, the same 3p orbitals, and so that extra proton makes silicon be a little bit smaller, and that electron is sorry, I'll be with you in just a second. So that electron is the silicon electron is held a little bit closer because of the extra protons. So hang on, Rid. Aiden says in the YouTube, I'm not clicked on myself so the viewers cannot see your screen. You need to click on the U icon in the bottom. Okay, give me a second. Aiden, which bottom are you talking about? So Aiden is letting me know that for some reason the YouTube, it's not showing my shared screen.
So in the
there,
Hangout,
does that work?
let me see.
It might, there might be a little bit of a delay, but I just clicked on U on the bottom there. So it looks like the YouTube is working in terms of voice, but maybe not working in terms of the screen yet. I'm gonna put the Hangout. See, this is crazy because the Hangout, I don't know if you can see that, but the Hangout is sort of this infinite, like the mirror, infinite. Look on the bottom right here. I clicked on U here to try and share that. There we go. It's working.
Yeah, Mr. Thompson, it works now.
Okay, good.
HS Tech.
HS Tech comes through again. Okay, so Rid, your question was about aluminum, and I kind of talked about silicon also. Look at sulfur, Rid. Sulfur, if you think about the electrons, sulfur is going to have 3p4. So that means that fourth 3p electron is going to be paired in an orbital. And so because it's paired in an orbital, it's actually going to be easier to remove because of a little bit of repulsion between those electrons. And then it goes back to the normal pattern. So it's the discontinuities that give us some extra insight into the energy, into not only the energy levels, but the orbitals within the energy levels.
So AL is smaller because it's a new orbital, and then like S is there because of the repulsion.
Correct. Yep. So those discontinuities happen for two different reasons. All right, I'm going to go check Twitter and see if there are any questions. Doesn't look like there are any questions yet from the Twitter world. So those of you that are on the Hangout, let me know if you've got a question. Here's one from Leo. For question 12 on the first topic 4 and 14 quiz, you ask about an explanation for hybridization in C2H2, and you wrote that I missed something about excitation. What was that again? Okay, I'm happy to help you with that. Let's see, topic 4 and 14 test. Okay. Oh, I don't see that here. So that's because I'm in the wrong spot. Sorry, I'm just talking to myself. I need to find the right folder. Give me a second. Topic 414. Let me find the question. Oh, yeah. You sure that what, Leo? You sure that wasn't the? Yeah, Rid, I haven't forgotten about your question. Leo, are you sure that wasn't the topic 212 test?
It says quiz 1 colon topic 4 and 14.
Oh, you know what? I think that's a misprint on my part. I think I just to start the quiz, to set up my quizzes at the top, I just kind of cut and paste from a previous quiz to get the right formatting, and I think I might have just forgotten.
Okay.
What are the questions about? What's the first question?
First question. It has questions about hybridization and Lewis dot structures.
Oh, yeah, that makes sense.
Yeah.
Okay. Let me see if I can find it then. Quiz topic 4. Okay, so on the screen now, I have, so Leo's question was about the hybridization of C2H4 or C2H2, and on his, Leo, I'm not trying to call you out, but you wrote it on your question here. I didn't give you a mark because you forgot about the excitation. So carbon, and it's not going to be perfect, but I'm going to try writing here. Carbon has 2s2, and then it has 2p, and so here's a 2p, here's a 2p, and here's a 2p orbital. Carbon has, and this is 2s here. Carbon has 2s2, 2p2. This electron, so let's see if I can, this electron here, okay, here's what I'm going to try. Bear with me. I'm going to try to make these electrons far enough apart. Nope, didn't happen. This second electron has to be excited in order to spread out so that it can fill the hybridized orbitals and the unhybridized p orbitals. Those electrons have to spread out. It says here the orbital diagram, the Mark scheme says orbital diagram representation of carbon ground state going to carbon excited state electron configuration. It costs energy to excite this electron. However, the forming of the bonds releases energy. So that releasing of energy releases far more energy than it cost to excite that electron. So I hope that helps a little bit. Kunwu, I see you got a question from Ryan there. Rid asked a question about electron configuration for Rid asked about the electron configuration for ions, and I'm guessing you're thinking of ions like transition metals. Okay, so if we think about, let's pull up a periodic table. If I think about an element like vanadium,
ions as in like when like something with a charge.
Yeah. You're talking about electron configuration, right? So one of the things that people often missed on the previous tests had to do with the fact that it's the 4s electrons that are lost first. So I was going to talk about something like vanadium. Vanadium is, in its normal state, is argon 4s2 3d3. And if you want to make the vanadium 3+ ion, it's going to be argon 3d3 because it's going to lose transition metals, lose 4s electrons first. I think that's a key. Rid, I don't know if that answers your question. I want to get to Pim's question because she asked it actually quite a while ago, and I've been kind of ignoring it. It's already 8:20 too, so I'm not sure I'm going to have time for all the questions. We might have to try again tomorrow.
Okay.
Rid, does that?
Yeah, I think
the key is for transition metals. You got to lose the 4s electrons first. So if I give you another example, like copper. Copper is neon 4s1 d10. So copper 1+ is going to be neon 3d10, and copper 2+ is going to be neon 3d9.
You mean argon?
Oh, sorry, you're absolutely right. HS Tech.
No. Yeah.
So yeah, argon. Does that make sense, Rid?
Okay. So with like scandium, it'll be, well, we take out the 4s first, right?
Yep.
And then
Yep.
so it'll be like 3d1 if it's okay. Thank you.
Right. Scandium. If scandium forms a 2+, it would be 3d1 left over. If it forms a 3+, it'll just be argon, basically. Okay. Kunwu kind of summarized the list of questions, and I'm not gonna ignore dilution. The question from Rahul about formal charges. For that one, I might suggest going to the Mark scheme for that quiz first to see if that helps. But remember, in terms of formal charge, the formula is number of valence electrons minus the number of bonding pairs minus the number of lone pair electrons. But I want to answer Pim's question about dilution. So, Pim, can you give me a bit more specific in terms of what you need? Are you asking in terms of using C1 V1 equals C2 V2? Is that what you're referring to? So I'm going to pause for a second while I see if Pim is going to answer.
Okay. Last time we did like a lab in class, and we were diluting salt water and ACl. I can't find it.
I'll come up with a question on the board here. Check the screen here and see if this question kind of makes sense in terms of what you're looking for. How would you make a 150 milliliter solution of NaCl with a concentration of 0.60 excuse me, moles per decimeter cubed? Let's see. Oops. Let's see, moles per decimeter cubed with a stock solution that has a concentration of 1.4 moles per decimeter cubed. Pim, does that look like a question that you would want to have help with? So, C1 V1 equals C2 V2. And C1 is the concentration of the stock solution. C2 and V2 relate to the solution you are making. So solve for V, oops, I didn't type that very well. Solve for V1. So I have 1.4 times V1 equals 0.6 times 0.150. Think about what I've done here. I'm going to solve for V1, and on the right-hand side, C2 and V2, this is the concentration and the volume of the solution I'm going to make. So if I do the math here, let me see if I can find a calculator. If I do the math, I'm going to take 0.6 times 0.15, and then I'm going to divide by 1.4. The answer I get is 0.064, oops, 0.643 liters, which is 64.3 milliliters. That means I would need to take 64.3 milliliters of the original 1.4 of the 1.4 moles per decimeter cubed solution, and I would need to put it into a volumetric flask or a beaker of some sort, and then I would add water to get to 150 milliliters. Sorry, that's a superscript. Let me fix that. Okay. So Pim, that's a dilution where you're solving for V1, and V1 is how much of the original solution do you need in order to make the new solution. And also, just so you know, Siri just sent me an email and asked if you needed to know about ozone, topic 14.1b, like the ozone layer. The answer is no. You don't need to know about the ozone layer. You should be able to draw Lewis structures or resonance structures for ozone, but you don't need to know about the ozone layer. Pim, I hope that helps in terms of your question. Next was dative bonds. So a dative bond is a bond where both electrons come from one element or one atom. And maybe one of the classic examples of a dative bond is H3O+. I don't have a good way to, let me see if I got an idea. Let me see if I can find a good Lewis structure for H3O+. And then I can talk about it that way. This isn't too bad. This is let me copy the image here so I can put it into Word. It's maybe not the most elegant solution for all of this, but it's working for now. What I need to do is do this on my tablet so that I can share my tablet screen and then I can write on it. We'll have to try that again. Okay, so in terms of a dative bond, H plus is a proton that's donated from an acid. And if it bonds with water, this bonding pair and this bonding pair are already taken in terms of oxygen and hydrogen. And these two pairs here that I'm highlighting would be lone pairs. This H plus does not have any electrons, so it's going to share these two electrons and make a bond. And I don't think that this is my favorite structure because I would have drawn them as lines instead of using the dots for the bond, but that kind of gives you an idea. So a dative bond is used, here's a structure. A dative bond is used because this hydrogen doesn't have any electrons, and so it bonds with a pair of electrons that came only from the oxygen. Another classic example of a dative bond is carbon monoxide. There's a question about formal charges for nitrous oxide, and my thought on that was to go to the mark scheme about that. I hope that's not too bad. I'm going to have to go pretty soon here. There's a question about ionization energy equations. So if you want to do the second ionization energy of, let's pick an element, gold. I'm going to do the second ionization energy. So it'll be Au1 plus, and then, and this is a gas, and it's going to form Au2 plus gas plus electron. And if I really want to format these correctly, superscripts, right? I didn't ask if 8:30 was my bedtime. Pretty close, actually. I try to go to bed between 9 and 9:30, but I've actually still got more work to do tonight. And I've got a family that wants to spend a little bit of time with me. My son is about to go to bed. So here's the second ionization energy. Let me make this font a little bit bigger. This is the second ionization energy of gold. If I want to do the 10th ionization energy, my son doesn't really care much about chemistry, so I know it's not, he doesn't think it's quite as minty fresh as I think it is. If I want to do the 10th ionization energy of praseodymium, then I'm going to start with PR that has a 9 plus charge, and it's going to form PR with a 10 plus charge. So it's going to lose the 10th electron plus an electron. So the ionization energy, if I'm asking for the 10th ionization energy, it means it's going to form a 10 plus ion, and it has already lost 9 electrons. So I hope that helps a little bit there as well. 8:31. I'm gonna have to call it a night here. We can try again tomorrow. I think I'll have some time tomorrow, and if I try it tomorrow, I might try using my tablet, and that way I can write on the screen. I don't know what time yet. I have a commitment in the afternoon from like 3:30 until 5 or 5:30 or something, so it won't be that early. But I can try to do it a little bit earlier. Yeah, Leo, thanks. My tablet, I think, had the Google Hangout app. It wouldn't let me use it from my my Lowell T at ISB account, but I can just use the same. I can use the same lthompsonscience@gmail.com to try and create the Google Hangout. So let's say tentatively like 6:30, and I can do maybe an hour, hour and a half. And I'll try it on the tablet so that I can write on it. Well, I'm not sure how the screen sharing will work, but we'll see. We'll see if we can go from there. So thank you for everybody who is asking questions and here present. You're certainly welcome to send an email. If I have time before I go to sleep, I'll get to it tonight. If not, I can certainly get to it tomorrow morning. I do wake up pretty early. So have a good evening. I'm going to go say goodnight to my son. And thank you all. Keep it minty fresh.